Hi, everyone. So, as it says on the slide, my name is Jack Koenig. I've met many of you, but not everyone. So this here says 10 years of Chisel, and for those of you who know about Chisel, you will realize that that's wrong. The paper was published in 2012, but I have been working on Chisel for 10 years, so I get to have a grandiose title. So what is Chisel? I usually have a spiel here, but I don't have enough time for it today, so I'm going to skip it. So you should visit our website, see past talks on YouTube, and talk to me later if you don't know much about it and are interested. But what Chisel is it is now officially an award-winning HDL. The DAC paper got the most influential paper award, which is very exciting. Now, I am not on there, so applaud for them, not for me. But really, what makes it most influential is that, or makes it such an influential paper, is that so many people, whether they use Chisel or not, they use it as a reference point, they compare to it, they have built other things that they think are better, and that's great, and that's like what you want from work, right? You want it to inspire other people. So that's pretty awesome. Just for the people who are Chisel users here, hot off the press, Chisel 7.0 is out. I haven't announced it yet because I wanted to announce it here. I should have released it here. I forget about that OrComp tradition. That's a good one, but anyway, I released it like 2 days ago. But it's got a lot of new things or improved things like probes, which are XMRs, properties, which are metadata, layers, which is kind of a better way of dealing with with having verification code that you may or may not include with the design code, and it can lower to like if-defs. It can also lower to system Verilog bind. There's a lot of other stuff, format strings, module prefixing to get around the lack of namespaces in Verilog. There's a pretty big improvement to memory use. Better stack traces. We now have a statically linked fir tool if you're like us and running on really old Red Hat, because that's apparently what everyone in the hardware industry does. And then there's some experimental APIs with inline unit testing, which I don't have time to talk about, and formal contracts. But I'm going to skip past that. We should talk about that later if you're interested. So what is the purpose of this talk for the next 8 minutes? Is I have an opportunity with a captive audience to share my obvious wisdom, or perhaps they're just bad opinions about what I think matters in an HDL. And I have these opinions. I'm not sure that we always do the best job of all of them. So some of these are aspirations as much as they are suggestions to anyone else here who's interested in working on HDLs. So I suspect there are people here who want to make their own HDL. I know there are many of you who are working on your own HDLs, and that's great. And I could talk for a very long time about how important it is to leverage the work of others. That's why we do open source. We do it to collaborate. If you're embedding in a language that already has an embedded DSL, you should consider using it. But we have many in Python, and we have 3 in Scala. So this isn't always the case how it ends up. But let's say you have a very good reason to not use what already exists. As far as the existing DSL, you should at least consider trying to use an IR. Whenever we had the original Scala Fertile compiler, which is our compiler underneath Chisel, and I maintained that. And then when we transitioned to the Circuit Fertile compiler, different people took over Verilog generation, and that is one of the best things that's ever happened to me. You think it's fine and easy to generate Verilog, I promise you you're wrong. Once you do it for long enough, it's miserable. And it's really nice to have someone else solve that problem. But what I'm going to say that if you are interested in making your own HDL that you should focus on are, unfortunately, the boring things. Getting started, the very basic syntax, and debuggability. None of that is the reason why you are ever interested in making your own HDL, but I think, unfortunately, if you really want people to use it and like it, I think those are the crucial things to think about. I also think you should watch Rashid's talk from LatchUp, where he kind of gives an overview of what embedded DSLs are at kind of an abstract level. I think it's the best explanation of that I've seen. All right, so when it comes to making a language, like an HDL, ease of use really matters. So these are very absolute statements, but I want you all to consider as we go through the rest of this, why do people like Python? What is it about Python that people actually like? And why don't people, at least stereotypically, like Java? Like, why are those very common opinions in the software industry, and probably opinions that many people here hold? Maybe some of you disagree. I personally don't particularly like Python, but that's a whole separate discussion that we can talk about later. But a lot of people like it, and there's a good reason for it. So one of the first things that I think is the most important is getting started. So for most people, you have like 15 minutes of attention if you're lucky when they look at your website to try it out. And if they can't figure it out that quickly, probably even less, you're done. A quote from someone here in the audience said, "I tried Chisel years ago, but I couldn't get it working, so I gave up." And really, Chisel has been kind of hard to use for most of its history. Like, you have to go install a build tool. You have to make sure you have an updated JVM. You have to do all these things. So nobody likes build tools. Whenever you're writing software or hardware, you're trying to do what you're trying to do. You're not interested in the build flow. But generally, when we install things, you have to deal with that to some level. So ideally, a prospective user would not even have to install a build tool, but if they do, then they shouldn't have to configure it, at least for the basic introduction. Of course, customizability matters, but when you have a landing page that says how you should do something, you should not have to do any configuration. And ideally, you should be able to try it out in a browser. And I want to give a shout out to Surfer, because Surfer, like literally the first thing is an example that you can use. And similarly with Spade, it works right there in the browser. That's a great way to do getting started because people can try it immediately. We used to have Chisel in the browser. We don't for various reasons at the moment, but it is still really easy to use by one download. You download, this is on our website, so you should check it out. You download Scala CLI, and then you can just curl this example, and then you can run it, and it will do something interesting. And that's like so much better than what we had in the past. I think that kind of thing is really important. Okay, now moving on to syntax, which is something that everyone has very strong opinions on. But here I have hello world in Java and in Python. And this is one of my arguments for what is it that people like about Python is, I should have said this on the previous slide, people like it because it's so easy to run. You just type Python in your terminal, I guess Python 3, in your terminal, and something pops up that you can use. Well, looking at, now and when you want to run Java, it's a lot more work. Well, what about syntax? Like the hello world for Java is like a lot of text just to write. And that's not very information dense. It's not very useful for the purpose of printing hello world, whereas in Python, you write print hello world and that's it. Of course, you will then build things that are more complicated, but that kind of very basic introduction, I think, actually matters a lot. Now, a counter argument that many of you probably have and are not wrong to have is that you'll say that code is read many more times than it's written, and so when things are too concise, that's bad. I think that is true to some extent, but when you have like really pithy syntax, when things are very concise and information dense, it can fit on a screen, because if it can't fit on a screen, it can't fit in my head. Maybe you're a lot smarter than me and you can scroll through this long thing and internalize it all, but I can't. It fits on a screen or I can't reason about it. And so to me, I actually think that the syntax of your language being concise enough to fit in being relatively information dense is really important. If this is something you want to fight or chat about, please see me after. And then the last one is where I think debuggability is really important. So the best possible debuggability is waveforms and source level debugging, which is a lot of work to do. And again, kudos to the Surfer folks for taking steps in this direction, because what most of us mere mortals will do instead is just embrace the fact that Verilog is what the tools support, and so Verilog is something that you're going to have to make look good and make debuggable. For better or worse, the proprietary tools that most companies are using have really good debugging support. They have these GUIs where you can be stepping through the Verilog and you can see like what value each signal has on a given cycle, and that kind of thing is really powerful. So if you want to create an HDL and you're needing to target Verilog, then you need to make sure that the Verilog is a good representation of your HDL. And the things you need for that are source locators. Good error messages is sort of related to that, and Verilog names. So on source locators, if you're thinking about making this is not possible to do in all languages. Like not all languages have a way for you to grab a source locator. And so if you're thinking about doing this kind of thing, you need to make sure that's possible. So here's an example from Chisel, where when you write this Chisel, we will give you relative path source locators, lines and columns to everything. That information is really important for mapping back from the Verilog to the source code. But it's also important for your error messages. So carrying on from source locators. So good error messages are really important. If your new users do something wrong and they get an error and they can't figure out the error, then they're going to leave and they will not come back. So what I did here is I made a very simple error in Chisel, and then on the left, I messed with it a bit. I disabled all the stuff that we do, and I made it give a stack trace to show what would the complete raw stack trace be if we were doing a really bad job. It would look like that, which is absurd, right? Nobody, for what this error is that you don't know what it is yet, should be looking at that error message. This next one is, okay, let's say I do need to give a stack trace because Chisel is embedded in Scala. The user's source code will be on that stack, so sometimes a stack trace is useful. So there are things you can do to process that to make it simpler. So this is the same stack trace as the one on the left, but with the actual processing that we do. And all of a sudden, it's got like 3 of those lines are from the user's source code. So you need to make sure you clean up any source locators. And you might see this error message, high index is out of range. So really, most of the time, a source line and a caret, it looks professional, it's easier to debug, and it will make your users much happier and much more productive. And so this is the actual error, and you can actually figure out what the bug is, thank you, from this because it has the source line in it. And that's pretty handy. This is not that hard to do, but you need to have source locators to do it. Thus my previous slide. And then finally, I'm gonna just touch on good Verilog names because this one is really hard to do. Having worked on this for a very long time, it's a lot harder than you ever think it's going to be. But as I said, most users are needing to debug the generated Verilog, so you need to propagate that information from the source to the output. But if you're doing something like Chisel that's a generator, it's really easy to have name collisions. And so there's also work you need to do to minimize that. And so this is not the best example in the world. I was coming up with this earlier, so it could be better. But what I have here is a function that will create, it's gonna take an argument, add 1 to it, delay it by 1 by putting it through a register. And I'm calling that twice with 2 different inputs. And the key thing that I'm showing here is that in Chisel, this name, out0, shows up, and delay, the name of the register, shows up. And so because we are prefixing all values created in this function, we're prefixing it with the left-hand side of this connection operator, it's showing up in the Verilog. And so the fact that I call this function multiple times, in much older versions of Chisel, you would have gotten, well, in original Chisel, you would have gotten T1 and T2. And then in somewhat better versions of Chisel, you would have gotten delay 0 and delay 1. But now you get something that is like much cleaner, much easier to understand, much more stable. And so if you were thinking about doing something like this, you gotta focus on the Verilog names, and this is where it's also useful to leverage someone else's work because the compiler, any compiling you do also has to propagate all this information, so there's a lot of work in Circuit, the compiler that we use in Chisel, to do this. So that's my talk. If you're interested, please check us out. And I guess I have a couple of minutes for questions.
Thank you, Jack. So, about these good Verilog names, I would say that's only needed when you need to have view the Verilog. I think the ideal step, would be that you could do debugging on your Chisel level and you don't have to go to Verilog and you don't have to look at the Verilog. I think that's the final step for this last topic. But what's your opinion on that?
Yeah, no, I agree entirely. I think source level debugging is what you want if you can do it. And it's a lot of work. It's a lot more work than even that. And so and also, a lot of people are going to use Verilog no matter what. We are an IP company. We sell Verilog. They want the Verilog to look good. So there are many other reasons for it, but you're right. Source level debugging is better.
You still need good names. How do you, if you don't have good names, how do you find your longest paths back in the source?
That's true, yeah. So, for example, when you are looking at your synthesis results, those names are going to need to get relayed back, which means you need good names at whatever's feeding your synthesis tool. Like even if there's no Verilog involved, if you go straight into these tools, the names show up in later error messages or later reports.
What do you generate for source locations?
If you could propagate the source locations through like proprietary synthesis tools, that would be great. So, I mean, I don't know if Yosis can do this, but that would be really handy.
I think I remember a meeting where one of the proprietary vendors was interested in source mappings. Is there still interest from proprietary vendors on source mappings or even directly working with Circuit?
There has been work on that in the past. I'm not closely involved in it, so I don't know where it is. I think it's one of those things that it's a side project or a secondary project and it may fall off, but yeah. So I don't have any like specifics, but that is a thing that people are still interested in.
Just an easy open question. How do you see the future of Chisel?
Easy question, that's a hard question. No, I think that like the problem is always verification, and so most of our current work is related to verification. I didn't focus on that today, but I mentioned some features. So like layers and probes are both verification related, and then we have all this work on inline unit tests, which what it's really getting at is making it to where you can ensure that you can write tests that when you compile a large Chisel design, that you're running unit tests on the same Verilog that you're going to tape out. That's a very complicated topic, but basically, like, it's all about verification and formal verification as well.
Thank you, Jack.
All right. you.